All right, so this next topic, really, we're getting into sort of what do we do with these stats methods that we sort of learn in here, and we're going to spend a lot of time talking about more advanced things like t-tests, ANOVAs, and these kinds of tests. But a big part of statistics is just trying to summarize data and use methods like sort of data displays, graphs, that sort of thing, to really look at how data can be summarized and recategorized in ways that make it easier for people to understand sort of what's going on in the data sets. Let me see if I can bring this up. Let's see if it'll work in this format. So one thing that I was encouraged to do that's in these slides here, if you click on this CSUN Counts website, which I won't go to here right now, but there's a couple different ones. There's CSUN Counts is a website that actually just click on it so you can see it. That will show you you can actually go through and explore different things, different information about our campus, about the students. You can look at sort of dashboards about characteristics of all students, for instance, if you want to know what are all undergraduate students sort of like demographically. You can actually go and play around with data. This helps you to sort of summarize things, and it does some additional analyses and things, but you can sort of play around. You can look at right now, these are head counts, so just numbers of different majors. You look at different majors, this is fall 13 to fall 19, okay? And look at the difference, between them. How many, education versus business versus arts and media versus social behavioral sciences, right? We tend to be one of the largest, with business being sort of close after for the most part. Sometimes they're bigger, sometimes we're bigger, but we tend to be fairly similar in size. Okay, some people ask you, I get questions a lot. Well, how big is CSUN? How many students are there? You want to know how many people are in your major, or at least in your college. You can do that. You can also right now it's departments all, but if I wanted to look at just psychology, I could just break it down here and get just psychology if I wanted to. All right, so if you want to know, roughly how many psychology majors there are, this gives you an idea. So right now, as fall 2019, roughly 2,500 psych majors. Okay, you can do that for any of these departments, or you can break it down all kinds of ways. Anyway, so that's one way of thinking about it. You can look at this. There's also another link here if you'd like. I'm not going to go to it just for time, but there's a link here. This is all of CSU. You want to look at CSU's. I guess you can. This is faculty login. Okay, all demo in class. So maybe I'll do it so you can see. High school community college CSU by the numbers. Let's see here. There's a public dashboard. All right, cool. There's a public dashboard for Cal State. You can see, all right, here's the year students started and the percent of students who graduate within 6 years. So you can actually go through and explore data about the CSU system and see what's going on. More importantly, more interestingly, I wanted to show you this down here. I would, if you have time, go through and click on this and just sort of play around, because there is a lot of cool, just trippy data sets, 17 plus impressive data visualization examples to see. This is one of my ones actually it's down farther, the actual map. So this one is interesting because this is basically looking at showing what people are doing throughout the day. And right now it's not going. So let's go medium fast. So it goes a little faster than that. So there's a way they visualize sort of where people are and what people are doing at different times of the day. And people traveling to and from a sport event or from work and all over the place. People waking up at 5. Go even faster and see. Actually, they're able to visualize sort of where people are and sort of how they're traveling around. There's actually a pretty cool graph and sort of how this stuff is working. Now I got to go in fast, so it looks like just craziness, but you can sort of see where the explosions are. Most people are here at work. You got some people working in education. You got some people in leisure activities, which shows you where everybody sort of seems to be different times. Let's go back and look at something else. You got world's biggest data breaches. You got dog breeds. History of the NFL, if you like, sports, football. Got a who's fighting whom in Syria. Recession and reshaped economy. The other one that's kind of a cool way that they do stuff is sort of looking at the relative size of things. This is an interesting graphic because again, you can just sort of talk about how big things are relative to other things. What this scale does is it puts everything into a comparable scale, so you can actually see where things are. Not everything, most everything. But it's a kind of a cool way of looking at and graphically displaying differences in size across multiple objects that you don't normally see side by side, and get an idea of what is bigger and what is smaller. All right. So it does. Let's skip. Just want to show you it. Shows you a whole bunch of stuff. It's coming back down kilometers, all the way down to very small things down here. You can look at. So here's a person. Mankind. Can give you some information on a person. So relative to a sunflower is a bit larger. Alright, so as we move the scale sort of outwards. Let's see, let's go over here. Actually, that's way too far. Let's do back here. Let's see, like, alright, here's an atom. So here's a millimeter. Here's a millimeter saw. A sesame seed. There's an ant relative to a sesame seed. Getting the centimeters. Getting into like a memory card relative to to a bumblebee or a housefly. Getting into meters now. Actually, let's go back. It's too much. You can see the size of an elephant. And I think you can. Yeah, if I just sort of scroll my mouse, it'll go a little bit at a time. So there's an elephant relative to a double-decker bus. The height of a giraffe. There's the Sphinx. There's a blue whale. It just says whaling blue whale. There's the Triumph Arc. There's a jumbo jet. Right, keep going out. You got the Ferris wheel. You got pyramid. You can sort of see now how the sizes are. Here's the Cologne Cathedral. Here's Rock, the Empire State Building. Burj Khalifa, Angels Falls. You just keep going out. It actually takes you all the way to the size of here's Mount Fuji relative to Mount Everest. And you can click on each one of them. It'll actually give you information about it in terms of size and height. You keep going out, keep going, keep going, keep going. Then you start to get the planets. There's the Moon, Mercury, Mars. It gives you sort of relative size of all kinds of stuff. All right. So it's something I would say, go out and play around with some of those because they're really, sort of interesting, different ways in which people are using sort of graphics and analytics to sort of demonstrate data and how data works. Okay, so I had to get out of the web app thing there as the music was playing, and it played through the rest of the slides that we went through. In class, so I'm redoing it so it doesn't have all that audio on there because it was literally overpowering what I was saying. So I'm sort of redoing these so that it doesn't have all that noise. So, we went through a couple of these examples. Some of the examples didn't work, which is a whole other thing. That some of these data visualization options, they're really cool and they're complex, but that complexity. They're complex in terms of taking a bunch of different data and making it sort of accessible. But that complexity also leads to other issues like compatibility with web browsers and other things that become more complicated. But there's a lot of really cool stuff. You know, click on these links, check them out. Especially this, just go through and look at these things. There's just some really cool things people are doing with data nowadays. All right, so let's go forward. So these previous examples that we have, they're, you know, that we just went through those links, they're advanced. They're sort of what you can do and where you can get to with data analysis. Let's start back at the beginning. Let's do some simple things. Like, you know, how can we make data more palatable for people to, you know, to be able to get meaning out of the data? And how can we make data useful, make it helpful, make it meaningful for people? Which also brings up another topic, that how can we actually, you know, you got to make sure you're using it and not trying to mislead people, which often happens as well. You know, in the pandemic, during this time, it's sort of an interesting historical time that we're going through. And one of the things, of many things you can notice, is that you'll see people posting different graphs, using the same information potentially to argue that things are getting better, things are getting worse, that you know, we're having more deaths, less deaths, more infections, less infections, and yet it's the same data, and yet they're somehow changing, manipulating data to give out different information. So it's another reason why to sort of have a critical eye about information that's being provided, regardless, and sometimes maybe not regardless, of the source in which they're coming from. So how can we make data more meaningful and use it to sort of get information across to people? So what the point is here, but realizing that it can be used like for evil as well, right? Okay. So this was data that I collected from students during the spring semester of 2018, and it's just their heights. I just asked them to fill it in. So it's self-report. Didn't go through and actually measure everyone, but it's a self-report of student heights in inches. So, you know, there's, if I remember correctly, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 22. That's 33. So we're one shy of 44. So we got about 43 participants that responded to this survey at the time. So keep in mind, there's 43 responses about height. All right, we look at this and you're thinking, great, it's a bunch of numbers, a bunch of heights. What am I supposed to do with that? So then the big question is, well, so how do we make this not more interesting necessarily, but easier to sort of digest, easier to start looking at sort of, are there any patterns? Are there types or certain heights that are more regular, more normal, more popular, whatever the term you want to use, that sort of occur more often? What was, you know, who's the tallest, who's the shortest, you know, what's the range? And we can sort of go through and pick that out. Looks like there's some 73s in here. Anything above a 73? And it looks like maybe the shortest, you know, but it takes a moment. You got to go through and figure it out. Looks like maybe 61 might be the shortest. A couple 61s. Oh no, there's a 60. So, you know, we got to go through and figure out. You know, go through and sort of weed through the numbers. And this is 43. Imagine this is 430 or 4,300. The more data there are in a set like this, in a data display, data matrix, the harder it is really to sort of look for patterns and really find anything meaningful in it. So we got to figure out ways to sort of transforming this into something that's more useful. All right, so if you're going to try to do anything, make graphs, display data, do anything with the data, what's the first step? What do you got to do first? So before we can really try and get any meaning out of the data set, the first step really is let's at least put it in order. Try and find some relative order to the data so that it you know, we can get some meaning out of it. Let's see if I use blue, will that work? Let's see well. So we're going to go through the numbers here and say, okay, there's a 57. So I missed that 57 before. So it looks like maybe that's the shortest person. 57. I don't see anything else even in the 50s. So, all right. So put it in order. So instead of just having it in the order that it was in, let's do, all right, so here's 57. right? And then we can go down and say, all right, 57. What's the next? So let's cross off 57. We already got that one. Cool. Let's go down. What's next? Maybe 57 to, I think maybe 60 is the next one. There's a 60 here. Okay, 60. All right. And there's another 60 up here. Any other 60s? I don't see any other 60s. 61. Okay, there's one 61 here. All right. So let's do a 61. Is there another 61? 61, 61. One there. Right by my ear. 61. All right, so there's a couple 61s there. I don't see any other 61s. Let's go to 62. So we're seeing 62s. There's one 62 here. All right, you have 62s in this column. I don't see any. Oh, 62 right here. So another 62. So we got 1, 62, 2 62s. Now, if you were using something like Excel or a program like that, you can simply just sort of highlight the data and ask it to sort it, put it from lowest to highest. That would save us a lot, save yourself a lot of time doing this. But in a sense, you would want to do this and continue to do it and find fill out all the numbers in order. To save some time, I'm not going to go do that whole thing, but you can imagine sort of going through the same process. Take all the numbers, make sure that they're represented in the table, and put them in order. But I'm going to erase this for a sec, and I can show you that on the next slide I've already put them in order, so that can make things a little bit easier. Make sure that I don't miss any numbers. Go look at this, and here we have all the numbers in order all the way down. Okay, so if we continue doing the process that we were doing, we would actually come up, with something similar to this, where we have the 57's the lowest number. We have two 60s, two 61s, two 62s, four 63s, looks like five 64s, four 65s, four 66s, three 67s, three 68s, one 69, 170. We have five 71s, two 72s, and four 73s. Okay. Now you can see with data like this, so it ranges from 57 to 73. But there's also a lot of redundancy. All right, so we have 157, great. We have two 60s. So the fact that we have 60 twice means it's sort of redundant. There's probably a better way. There's probably a better way to organize this so that those pieces of information are separated. And that's what this ungrouped frequency distribution does. It says, all right, let's look at all the values that we have, starting up here. So the lowest value, 57. Okay, then we have 60, 61, 62, 63, 64, 65, it's a horrible 5, 66, 67, 68, 69, 70, 71, 72, and 73. So those are all of our values that we have, and without any redundancy. So we're just placing each one in there once. And if I really wanted to be thorough, what I could do is do 57, 58, 59. Even though we don't have any 58s and 59s, we could include those and just indicate that there's zero frequency, right? So I can shift these down if I wanted to and do that. Not going to. I already got it written out, but that's one way you could do it. So we got the frequencies. So now, sorry, we got the values. Now we just got to look at the frequencies. All right, we had 157 and two 60s. Two 61s. I have two 62s. We have four 63s. Five 64s. Four 65s. Four 66s. Three 67s. Three 68s. I have 169. I have 170. I have 2, 4, 5 71s. Two 72s. And three 73s. So there's our frequencies of each one. So with that, I can now start thinking about the percentages. What percentage of each of the total data? Remember, the total down here should be, I should have 43 total values. So I can go through this and I can start to look at the frequencies relative to that total, and we can figure out the percentage. Okay, so let's do that quick. So if I have a frequency of 1, that means that my 57, my lone 57, is 1 divided by 43. All right, so this says percent is frequency over total times 100. Okay, so 1 is about 2%. So let's say it's 2.3%. That's what it says. 2.3%. Okay, 2.3%. So any place I have a single digit like that, it's going to be about 2.3%. Right? So anytime I have a 2 divided by 43, it's about 4.7%. So I have 4.7% there, 4.7% there, and 4.7% there. And another one down here is a 4.7% there as well. Okay, so there's all my 4.7s. So let's do 3s. 3 divided by 43 equals, this is about 7.0%, because it's like 0.6976. So say 0.07, so 7.0. So anytime we have 3s, we're getting 7.0% for that. Another 7.0% for that. Oops, I wrote down 70 instead of just 1. So it should be 70. There's 170. So that should be just 1 as well. So this is another 2.3%. Okay. So that was, I'm missing 1, 3 down here. 7.0%. Okay, so we got all those percentages for 3s. Let's do 4s. 4 divided by 43 equals 9.3%. So 9.3 here. And 9.3% there. Another 9.3 right below it. Okay. And then that's it. So now 5s. 5 divided by 43 equals 11.6%. 11.6%. 11.6%. And that's it, I think. So there's our percentages. So we can go on to the next one, the cumulative frequency. So the cumulative frequency really is, when you're talking about cumulative, you're allowing the data points to accumulate, meaning that if I'm looking at, say, 62, the cumulative frequency is how many scores are 62 or less. So I would take 2 plus 2 plus 2 plus 1, and that would be the answer for the cumulative percentage, or cumulative frequency here. Okay? So to do that, we're basically going to do that the same process. So because there's nothing lower than 57, the cumulative frequency here is just going to remain the same. It's 1. But now when I take that 1, add in the frequency of the next category, and we're now going to have 3 that is 60 or less. All right, there's 2 60s, 157, so there are 3 total cumulative frequency for those 2 values. So when I go to 61, I'm going to add those next ones. So 3 plus 2 is 5. 5 plus 2 is 7. 7 plus 4 is 11. 11 plus 5 is 16. 16 plus 4 is 20. 20 plus 4 is 24. 24 plus 3 is 27. 27 plus 3 is 30. 30 plus 1 is 31. 31 plus 1 is 32. 32 plus 5 is 37. 37 plus 2 is 39. 39 plus 3. Something's up again. This happened last time. What did I add up wrong? Let's see. 3, 4, 5, 6, 7, 11, 16, 20, 24, 27, 30, 31, 32, 37, 38, 39. Oh, I see the problem right here. Luckily, it's in the very last one. I wrote down there was 3 73s, when in fact there are 4. Okay, luckily it's like right at the end. That worked out. So, we now have 39 plus 4, which should give us the total cumulative frequency of 43, which is what it should be because that's the total. Okay. Can move these up a little bit so they're a little bit more aligned. So it should be 37 plus 2 is 39. And then this should be 43. Okay. 43. Great. Now we have the cumulative frequencies. We can then take and add up the cumulative percentages. You can either do that by taking the cumulative frequencies and dividing by 43, or we can add up the percentages. So let's try adding up the percentages and see if I can do this all at the same time. So 2.3 plus 4.7, that's going to be basically 5, 6, 7%. All right, so the first cumulative percentage is going to be just whatever it is for the first one. This is essentially just 2.3%. 2.3% plus 4.7, so 3 and 7 get like 1, they're going to say 5, that's 6, 7%. Which makes sense because we figured out that whenever we have a frequency of 4, actually that's not right. Oh, whenever we have a frequency of 3, that's 7%. Okay, so I can trust my math there. 7% plus 4.7%, that's going to be 7 plus 4 is 11, so it's 11.7%. 11.7 plus 4.7, it's going to be 11 plus 4 is 15. 7 plus 7 is 1.4, so it's going to be 16.4. Is that right? So the cumulative is 7. Let's check just to make sure I'm not getting off, because once you get off, the rest of it's going to be all screwed up. 7 divided by 43 equals 16.3 is what I have here. So that's maybe just because of rounding. 2.3 plus 4.7 is 7. 7 plus that, so that's 7 plus 4 is 11. Plus the 0.7, so 11.7. Add 7 and 7, I get 1.4. Add 4 and 11, I get 15 plus 1 is 16. All right, so far so good. So it's going to be a little off because of the rounding. So we rounded to 1 decimal place, so I expect it's going to be off likely in that 1 decimal place. If I really wanted to round to 1 decimal place in the end, I should be carrying 2 decimals or more so I can round up to 1. But if I'm carrying 1 the whole time, it's likely going to be a little bit off at the end. That's okay. So 16.4 plus 9.3, so the 4 and the 3 make it a 0.7 percentage in there, whatever it is. And then 16 plus 9 is going to give me 25%, 25.7%, I think. Sounds about right. 25.7, 11.6, so the 6 and the 7 is going to give me 1.3. 1.3. All right, so it's going to be a 3 there. And then 25 plus 11 is going to give me 36 plus the 1 is 37%, 37.3. Again, let's check it just to make sure, because sometimes you never know. 11.6. Should be 16 divided by 43 equals 37.2. That's what 37.3 is. It's pretty good. I think that's right so far. 37.3 plus 9.3. 3 and 3 is going to make 6. Like that. And the 37 plus 9 is going to give me 46. So 46.6%. 46.6 plus the 9.3, which means we're going to have a 0.9 here. Like that. That's a 9. My 9 in percentage looks similar. And then 46 plus 9 is going to give me a 55.9%. 55.9 plus 7 is going to give me 62.9%. Plus another 7 is going to give me 69.9. And then 69.9% plus 2.3 means it's going to be a 0.2 here. 69 plus 2 is going to give me 71, so 72.2. Let's make sure that's right. I should check it every once in a while. So 31 divided by 43 is 72.1, and I got 72.2, so it's close. 72.2 plus 2.3 is going to give me 75.5. And then plus 11.6, so the 0.5 and the 0.6 are going to give me 0.1. 75 plus 11 is going to give me 86, so 87.1. That 87.1 plus 4.7 is going to give me a 0.8. 87 plus 4 is going to give me a 91. Screwed that up somewhere. It's almost 92 plus 7. Let's see, 87.1 plus 4.7. 87 plus 4 is going to give me 91. Let's see, 39 divided by 43 equals 90.1. Oh no, I got 90.7, I got 90.91. 90.8. Hold on a second. 87. Okay, let's check it out. 37 divided by 43 is 86. This is 87.1. 32 divided by 43 equals 74.4. So somewhere something went off. 1 divided by 43 equals 72.1. So 72 plus 2.3. 72 I see. This is supposed to be 74. So somewhere I knew something was off. So this is 74.5, right? Because 72.2. 72 plus 2 is going to give me 74. The 2 and the 3 are going to give me 5. 74.5 plus 11.6, the 5 and the 6 is going to give me 1. And then the 74 plus 11 is going to give me 80. 74 to 85 plus 1 is 86. So 86.1%. Okay, figured it out, I think. 86.1 plus 4.7. Yes, it's going to be an 8. Like that. But it's going to be 86 plus 4 is going to be 90.8. Like that. Right. And I didn't adjust this. So 4 divided by 43 equals 9% instead of 7, because originally we had this as a 3, so this really should be 9%, 9.3%. That. So when I take 90.8% plus 9.3%, I get just over. So the 8 plus 3 is going to give me a 1. The 90 plus 9 is going to give me 99 plus 1, so it's like 100.1%. A little extra there is because of the rounding. Again, we were off a little bit in the first decimal because that's how we rounded. So that works out. That was a little mental math for my brain this afternoon. But you might think, why go through all this trouble? And of course, you know, programs like Excel and SPSS and whatever you like, R, SAS, there's lots of them. They all can do this stuff for you, but the whole point of getting to this is, you know, when you get these sort of, ungrouped frequency distribution tables, what you can do with them is now turn them into plots. So you can start to see how this will work. Well, I have a 57, I have one of them, so I can make a graph that's got, you know, a little 1 bar, and I can get, you know, 60 has 2, so it goes up to 2 instead of 1. And we can start to turn this into something that looks like a histogram, which is what we're going to go to next, which is on the next page, next slide of this, is sort of how to then turn this information into a graph.